Welcome back. In this video, we're going to start our unit on finance by talking about the time value of money. So we'll start off our finance unit by talking about simple interest, the most basic type of interest. Now, simple interest is something that some people don't think is actually used a lot because if you have a savings account, that doesn't earn simple interest. If you have a credit card, it doesn't charge simple interest, though each month it does. And we'll look at an example of that here in just a minute. But simple interest is actually the kind of basic building block of all other sorts of interest, as we will kind of see. So if you have a car loan, for example, that's simple interest. Your student loan, those kind of depend, but those are often simple interest. Mortgages are simple interest. There's actually a lot of different places in which simple interest are used. And in fact, anytime interest is compounded, we can always calculate one period's interest with simple interest. So compounded interest is really just simple interest calculated multiple times. So anyway, we'll get to compound interest, but let's talk about simple interest first. All right, so the simple interest formula is I equals PRT. Now, it's important to memorize both sides of this formula. A very common mistake I see in using this formula is students will memorize that simple interest is PRT, but they'll forget what's on the left-hand side. They forget what we're actually solving for. So what we are solving for is the interest amount. And so that is a dollar figure. We are solving for the interest amount. That is not going to be the final amount in the account after some period of time. It is simply the interest that is either charged or earned on an account after some period of time. All right, the principal, that's the starting amount. And that is also going to be a dollar figure. The interest rate, that's going to be written as a decimal in this formula. We'll get to where we use the calculator, and that's not written as a decimal, which is a little bit confusing. But anyway, in this formula, our interest rate is always written as a decimal. And then we have time, which is time in years. So we'll often have to convert time into years. So for example, if it said 24 months, we would put t in as 2 because 24 months is 2 years. So we'll look at a number of different time periods. So annually is once per year, semi-annually is twice per year, quarterly 4 times per year, monthly is 12 times per year, weekly is 52 times per year. And then daily is kind of a weird one because daily is typically 365, but can also be 360. Back before we had computers and calculators, 360 days a year was often used in interest calculations because it's easily divisible by the number of months, 12, and divisible by the number of quarters, 4, in a year. And so some financial institutions actually still use 360 to this day. In any of the problems you're working on, we'll always assume that there are 365 days in a year unless the problem specifically says assume a 360-day year. So anyway, all right. So that's our formula, and that is one of only 2 formulas you're going to need for this unit. So I would write it down. Maybe put a little star by it to indicate that it's something important to have written down. All right, let's jump to an example. So let's say you have a credit card bill of $850 with an annual rate of 23.99% interest. How much interest is charged for 1 month? And then what is the new amount owed? All right. So, like I said, credit cards don't charge simple interest, but to find the interest for 1 month, that is simple interest. So, our formula, again, I equals PRT. And so, I is what we're solving for. P is the principal, that's the starting amount, so that would be your credit card bill, $850. Times R, where R is the rate as a decimal, so that's 0.2399 instead of 23.99. And we want to know how much interest is charged for 1 month. And so time, we don't want to put 1 because remember time is in years. So if we put 1, that's 1 year. Instead, we'll put 1/12. So a month is 1 out of 12. Now, if it's over a year, you don't divide by 24. That's a common mistake I see as well. So if it's like 16 months, you don't do 16 divided by 24 to find the number of years. You always divide by 12. If you have a number of months, you divide by 12 to find the number of years. So again, if you had 24 months, you divide by 12, that's 2 years. All right, so we'll multiply 850 times 0.2399 times 1/12. And that's going to give us about $16.99. So that's the amount of interest that would be charged for 1 month on this credit card. Now, the next month, interest would be charged not only on the $850, but also on the $16.99. So that's what makes it compound interest. Now, if you paid that off, you wouldn't have to pay the interest, but it is compound interest if you don't pay off the interest every month. So the second question here was, what is the new amount owed? And so for that, we just take the $850 for the credit card bill and add on the $16.99 in interest that's charged. And that gives us $866.99. And so that would be the new amount owed. And the next month, interest would be based on this number rather than on the original $850. So there's actually a separate formula that we could use to calculate this number, but I feel like it's simpler to just memorize just the one formula, the simple interest formula, and remember that if you want to find the total amount, all you have to do is take the loan and then add the interest. It's pretty easy to do. So anyway, that's how we can find the new amount owed. All right. Now let's look at simple interest versus compound interest. Let's kind of compare and contrast what they are. So we'll look at a simple interest account and a compound interest account. And we'll assume this compound interest account compounds interest semi-annually. So that's 2 times per year. All right. Now, for ease of calculation, we are going to say that both accounts contain $100 and earn a very unrealistic but easy to calculate 10% interest. And we're going to look at what happens over the course of 1 year. So for our simple interest, for 364 days, the balance stays at $100 all the way through. At the end, we apply all 10% interest all at once. So we add our 10% interest. And 10% interest on $100 is $10. So after 1 year, it could pay out $110. So if that's the end of the time period for the simple interest, the account would contain $110. The compound interest account, which earns interest semi-annually, that's twice a year, that account, so twice a year, would mean that after the first 6 months, half the interest would be paid out. So 5% interest would be paid out. So 5% interest on $100 is $5. So that's $105 that the account would contain. And then the account will go the next 6 months, and then we'll be at the 1 year mark. And so then at that point, the other 5% is added. But now when that other 5% is added, that 5% is not calculated on the original $100. It's calculated on the $105. Now this doesn't make a huge difference. It adds an additional 25 cents because of the interest on that extra $5. So in this case, when interest is compounded, interest is being earned on other interest, not just on the original amount. So with simple interest, interest is always just paid on the principal. With compound interest, interest is paid on the principal plus any other interest that has been previously earned. So here our ending balance would be $110.25. Now, that doesn't make a big difference, but we also only started with $100 and only compounded twice per year. If we compounded more times per year, say quarterly, then we would only go 3 months before earning interest. And then for the next 3 months, and then the next 3 months, and then the next 3 months, interest would be earned on other interest. And so the sooner we start earning interest on other interest, the more money we'll end up with at the end. So quarterly interest would pay more than semi-annual interest. Monthly interest would pay more than quarterly interest, and so forth and so on. So the more often you compound interest, the more money you would end up with. So what is the theoretical limit of how much interest you could earn? Well, that is answered by continuous interest. So continuous interest is more often than every day. It is more often than every hour. It is more often than every second. It is an infinite number of compoundings per year. And so because of that, it uses a formula that you might be familiar with, A equals PE to the RT. That is the exponential growth or decay formula. And so we can use it to calculate the theoretical limit of how much interest you could make on something. So let's say we took our investment of $100. Actually, let's go through the different parts of the continuous interest formula first. So A is the compound amount. So this formula does solve for the final amount. So the compound amount is the amount that has been compounded. So it's kind of the ending amount. And that's what we're solving for here. So as a reminder, simple interest solves for the interest amount, not the final amount. But continuous interest, it does solve for the final amount. And then we have principal, our interest rate R, and then time T. So those are the exact same as our simple interest formula. All right, so let's use our same $100 investment. So that would be A equals $100 times E to the R. So we use 10%, so that's 0.1% interest. And then time was 1 year. So times 1. So we can calculate this in our calculator. 100 times E. So to get to E, you do second and then the natural log button. To the 0.1 times 1. And so what we end up with is $110 and about 52 cents. So $110.52. In this class, we'll always be rounding to the nearest cent. So nearest cent is 2 decimal places. Sometimes have people think that cent is 1 decimal place. Cent is 2 decimal places. So anyway, $100 or $110.52 would be the most that could be earned off $100 investment at 10% interest. So this is our second formula that we will need to memorize. So you might, again, want to put a star by it. And that's the only 2 formulas that you're going to need for this unit. Everything else can be done without any specific formulas. We'll look at actually one other formula, but I'll explain that when we get there. All right. So anyway, this is our continuous interest formula. Let's look at another example that uses continuous interest. So we've got an account contains $10,000, earning 1.9% annual interest, compounded continuously. We want to know how many years would it take to reach $12,000. So the reason why we're looking at how many years would it take is because this is a little bit more complicated to solve. So notice up here, 100e to the 0.1 times 1, that was really easy for us to solve. We just typed it into the calculator and done. This one will be a little bit trickier, and so let's look at why. So we'll have A equals P e to the RT. So we know A, that's the ending balance, in this case $12,000. And that equals the principal, the starting amount, $10,000. E to the RT. So our rate, 1.9%, so that's 0.019 times T. Well, we don't know T, but So we'll just put it as t. That's what we're going to solve for. All right, so to solve for t, our first step is going to be to divide by 10,000. So divide both sides by 10,000. Now we don't have to reduce that left-hand side. And in fact, if reducing the left-hand side gave us a repeating decimal or non-truncating decimal, then we would just leave it non-reduced. So in this case, we could reduce it to 1.2. So let's do that. So 1.2 equals e to the 0.019t. All right. So we don't want to round anything here until the very end. So again, if you needed to round a number on the left side, just leave it as a fraction. All right, now we want to solve for something in an exponent. And to do that, we need to use the inverse function of e. E, by the way, is Euler's number. It is just a number, kind of like pi. It's something we use a symbol for. It's something like 2.719, something like that. Anyway, it's just a number. But e to the x has an inverse function, and that inverse function is natural log of x. And e and natural log, or really any inverse functions, have the property that when they both occur, they kind of undo one another. So for example, if we had the natural log of e to the fifth, that would just be 5. Or if we had e to the natural log of 5, that would also be 5. So what e and natural log do undo one another. So just like, for example, if we did the square root of 5 squared. I don't know what the square root of 5 is, but I know that if I take the square root of 5 and then square it, that just takes me right back to 5. So anyway, that's what our natural log function can do. So we're going to take the natural log of both sides of this equation. So natural log of 1.2 equals natural log of e to the 0.019t. So that's going to give us natural log of 1.2 equals 0.019t. And so now all we have to do is divide by 0.019, and then we'll have t. So if we get our calculator and do the natural log of 1.2, and again, we don't want to round anything. So this is where you would put your fraction in if your fraction didn't reduce to a nice pretty decimal like this one. So natural log of 1.2 divided by 0.019. So notice we've not rounded anything. What we end up with is 9.595 or 9.596. If we round to 3 decimal places. So it would take 9.596 years, because remember that t is always in years. So it would take 9.596 years to reach $12,000. All right, now I want to warn you of something here. Some people will, every time they see the word continuous, will automatically try to use natural logs to solve the problem. That is not the case. We do not always have to use natural logs to solve continuous interest. In fact, we saw an example right here where we did 100 times e to the 0.1 times 1. We did not need natural logs there. So don't get in the habit of using natural logs every time you see continuous interest. We will only use it if we are solving for something in the exponent, the r or the t. So if you're solving for the rate or the time, with continuous interest, that part is also very important, then you'll need natural logs to solve. Otherwise, you will not. Now, we will only use this formula if it says the interest is compounded continuously. So don't use this formula if it doesn't say interest is compounded continuously, and only use this formula if it does say interest is compounded continuously. So very easy decision-making process on whether or not we use this formula. All right, let's move on to another example. All right, in this example, an account contains $1,000 earning 2.2% annual interest compounded quarterly. We want to know how much will the account contain in 3 years. And then we're also asked to find the contributions and the interest. All right, so this one says compounded quarterly. So it does not say compounded continuously. So we're not going to use either of our formulas. All right, so before we solve this one, let's kind of go through the different types of problems that we've talked about so far and how we're going to solve them. So simple interest is the formula I equals PRT. And it is just annual interest. So anytime you just see annual interest, that generally means it's going to be simple interest. Now, if it says annual interest compounded monthly, then that's compound interest. But if it just says 5% annual interest, that's typically going to be simple interest. The easy way to pick these out is it will not say the word compound in the problem. So picking out the simple interest problems is actually much more easy than people make it. So I will give you a little tip here, and that is to make sure you can figure out which problems are simple interest problems. Because typically some of the most missed problems on the test in this unit are simple interest problems. Because once we get past the simple interest, people tend to think, oh, everything is going to be compounded. And that is not true. So if it does not say how often interest is compounded, then interest is not compounded. So look for the word compounded in the problem to see if it is compounded. All right. So then we have continuous interest. Continuous interest is the formula A equals PE to the RT. And it will say continuous interest. Every time. Continuous or continuously compounded or something, some form of the word continuous has to appear in the problem for you to use that formula. So very, very easy to figure out which problems you should use that formula for. All right, and then we have problems that are compounded a finite number of times. And that's like weekly, monthly, daily, quarterly, any of those, where it's compounded a finite number of times per year. And for those, we're going to use the TVM solver. So that is TVM for time value of money. And so we will know these problems when we see the word compound. Anytime we see the word compound and it doesn't say continuous, we're going to be using the TVM solver. We're also going to be using the TVM solver anytime we have regular payments. And so we'll talk about that later on. But for now, we're going to use the TVM solver anytime we see the word compound when it's not continuous. All right, so let's jump back up. So an account contains $1,000 earning 2.2% annual interest compounded quarterly. We want to know how much will the account contain in 3 years. So it's compounded quarterly. That is a finite number of times, which means we're going to use the TVM solver. All right, so the TVM solver, we'll press Apps, and then select Finance, and then select TVM solver. All right, so N is the number of times interest will be compounded in total. So in this case, we want to know how much will the account contain in 3 years with interest compounded quarterly. So if it's compounded 4 times per year for 3 years, it would be compounded 12 times total. I%, that is our interest rate as a percentage. So in this case, we actually put 2.2. I actually wish the calculator wasn't designed like this. I wish it was 0.022 because that's how everything else works. But this is the way the calculator was designed. So all of our formulas, it'll be as a decimal. In Excel, it'll be a decimal, which we'll use Excel for our project a little later on in this unit. But in the TVM solver, it is as a percentage. All right, and then PV, that is the present value, that is the starting amount. So this problem says an account contains $1,000, so that is the starting amount. Now, in the TVM solver, money is directional, meaning it's either a cash inflow, meaning it's money coming to you, or it's a cash outflow, meaning it is money moving away from you. Now, when money is coming in, that's positive. When money is going out, that's negative. Now, this is a little bit confusing because when you put money into the bank, that's actually negative. It's still your money, but really you are loaning it to a bank. So that is actually negative. You're moving it from your possession into the bank's possession. So in this case, that $1,000 in this account is going to be a negative $1,000. So negative $1,000 because that is moving from the person who owns the account to the bank. Now, it says an account contains $1,000, not $1,000 is deposited into the account. And that doesn't make any difference. The timing is not relevant. The $1,000 could have been deposited today or yesterday or last year. It doesn't matter. It was still money moving from the person who has the money to the bank. All right, PMT, that we'll get to that next time. That is any series of regular payments. FV, that is the future value. That's the ending value, and so that's what we're solving for. Payments per year, compounds per year. That's P/Y and C/Y. That's going to be the number of times interest is compounded per year. In this case, interest is compounded quarterly. So if we just put 4 in for P/Y and press enter, it's going to copy it down to C/Y as well. In the real world, the number of payments per year and the number of compounds per year don't have to be the same, though in this class they always will be. All right, the last field on the TVM solver, payment end versus begin. And if you're not writing notes on these, I would recommend writing a note on this one, because otherwise it's going to trip you up. When we change the payment from end to begin is when payments are made at the beginning of the period, which is often specified in a problem, or when it is an annuity due. So if you see that phrase, annuity due, you're going to move the payment from end to begin. In this case, we have no payment. Our payment is 0. So it actually doesn't matter. We could put our payment at end or begin. Since we're making no payments, it doesn't matter. But our default will be end. So I would always leave it at end unless it says annuity due or unless it says payments are made at the beginning of the period. All right, so now we want to solve for the future value. So we'll move up to future value and we'll press the alpha button and then enter. All right, so it's $1,068.03. So $1,068.03. All right, so now we want to find contributions and interest. So contributions is how much did this person put in? Well, from what we know, they put in $1,000. So $1,000 would be their contributions. The interest, this is not complicated. It's not complicated to calculate this interest, although some people try to make it more complicated than it is. If someone puts $1,000 into the bank and then 3 years later withdraws $1,068.03, then that person earned $68.03 because that is the amount of money the bank put in. The customer put in $1,000. The bank added $68.03 in interest, which gave us the final balance of $1,068.03. So it's a very simple subtraction problem. Take the amount that was put into, or the amount that came out of the account, and subtract out how much was put into the account. That's your interest. All right, let's look at another example. All right, an account contains $5,000 invested at 2.1% interest compounded monthly. How many years will it take to reach $6,000? All right, so the last time we calculated how many years it will take to do something, we needed natural logs. But that was because that problem had interest compounded continuously. This one does not. This one has interest compounded monthly. So since interest is compounded monthly, we'll use the TVM solver. All right, so the way I usually like to start using the TVM solver is by clearing out the first 5 fields. So 0, enter, 0, enter, 0, enter, 0, enter, 0, enter. It won't let you zero out the payments per year or the compounds per year. If you do, you'll get an error. And that's the reason why we need the simple interest formula. Simple interest is just when we compound 0 times per year. But whoever designed the calculator did not think that should be an option. So anyway, also if we could put an infinity sign there for an infinite number of compoundings per year, we wouldn't need the continuous formula. But since it only accepts a finite number there, we can only use it for times where it is compounded 1 or more times per year. Anyway, all right, let's go up to the top. N would be the number of times interest is compounded. We actually don't know that here. So we'll move on to the next field. The interest rate is 2.1%, so we'll enter 2.1. The present value, that's the starting amount, so $5,000. The payment is 0, there's no payment, and the future value is $6,000. Interest is compounded monthly, so payments per year and compounds per year are 12. So those are both 12. And so we've put something in for everything except for N, where N is the number of times interest is compounded. So that's actually how we're going to find the number of years. So if you're ever stuck on a problem and you can't figure out what you're solving for, just start plugging in things to see what things you don't know. All right, now to solve this, we're going to hit alpha and then enter. Though I purposely made a mistake here. So you're going to see I'm going to get an error when I do this. So I got a domain error. So let's look at why. So notice what I have here is that both the present value and the future value are positive. Now, when the present value is positive, that means you start off by getting $5,000, not putting $5,000 into an account. So in many of our examples, the present value, if the present value is a positive number, that is a loan. So essentially what this would say is I'm starting out with a loan of $5,000. I'm not putting any money in. I'm not paying back the loan. And then I want to know when my account, which I have put no money in, and in fact withdrew $5,000 that I didn't have, when will that be $6,000? And the answer to that is never. That's unfortunately not how things work. So we need to make that negative $5,000. Now when we solve for N, it will give us an answer. Because the idea is that if you want to get $6,000, you need to give up $5,000 now or loan that to a bank at some interest rate to be able to get $6,000 back later. All right, so alpha and enter to solve for N. And what we get is 104.27. Now, what are our units here? Well, remember that N is the number of times that interest is compounded. So in the units for N will change based on the problem. If we were compounding annually, N would be number of years. If we were compounding semi-annually, N would be the number of semi-annual periods. In this case, N is we're compounding interest monthly. So N is the number of months. So this tells us that the number of months is 104. So from there, we can calculate the number of years pretty easily. And we can actually do that in the TVM solver. If we move to the end of this field, we can actually just hit divided by and type in 12. So we take the number of months and divide by 12, and we get the number of years, 8.689 or 8.69 rounded to 2 decimal places. And that's 8.69 years. So that's how many years it would take to invest $5,000 at 2.1% interest compounded monthly and have that turn into $6,000. All right. One more thing we're going to talk about in this first video on finance is APY, or annual percentage yield, which is also sometimes called effective rate. And really, that's just marketing. The difference between those two terms is complete marketing. They are the exact same thing mathematically. The reason why there's a difference, annual percentage yield is generally used on deposit accounts. So that's like a savings account or a money market account. Anything where the customer is earning money. So yield is the amount of money the customer, or the percentage the customer gains every year. And then effective rate is typically used for loans, just because it, I guess, sounds better. So anyway, mathematically, they're the exact same thing. You'll see examples with both. Just know they're the exact same thing. So both of them are the percentage change over 1 year. So just how does money change? How does the value change over 1 year? So in an earlier example, we looked at an account that contained $100. And then at the end of the year, so it earned 10% interest, compounded semi-annually. So after 1 year, 5% compounded semi-annually, it contained $110.25. So is the difference between those two things 10%? And the answer is no. The difference between those two is not 10%. It was 10% interest, but because interest was compounded, the effective rate is actually higher. The difference between those two, we could actually calculate very easily. $110.25 minus $100 divided by the original $100 gives us, and this is actually pretty easy math, we gained $10.25 on $100, so that's 10.25%. So that would be the effective rate, or the annual percentage yield, of an account where that charges semi-annual interest for 1 year. So that's what annual percentage yield is. It's just the percentage change over 1 year. Now, you don't necessarily need to memorize this formula, but you do need to know that annual percentage yield and effective rate are the percentage change over 1 year. So, in some of your examples, you'll be asked to find the annual percentage yield given the starting value and the ending value, or the amount of interest that's earned. In other examples, we'll be asked to convert interest rates. So let's look at something like that. So in this example, we have two loans. One that is 8.9% compounded monthly, and the other is 9% compounded semi-annually. And we want to know which loan charges less interest over the course of a year. So we know which one charges a lower percentage, but they're compounded at different frequencies. So interest compounded monthly, that's far more often. So that's going to generate more interest. Semi-annual is going to generate less interest, but also the interest rate is higher. And so both of these have some pluses and some minuses. And so what we want to be able to do is say, okay, what is going to be just the percent change from the beginning of the year to the end of the year? Because that would tell us which one you would pay less interest on. And so to do that, we actually have a function in the calculator, the EFF function. And so I'll pull that up here in just a second. But what it looks like, there's a little triangle, EFF. That's what the function looks like. And what we're going to put in it is the interest rate, so I%, and then C/Y. So that's what we'll put in the effective rate function, where C/Y is the number of compounding periods per year. All right, so let's go ahead and pull up that function. So we'll quit out of here. We'll go to apps and then finance. And then rather than selecting TVM, we're going to go up to triangle EFF. So our first one is 8.9% compounded monthly. So we'll have 8.9. Oops. This should be I% comma C/Y. Sorry about that. So our interest rate, 8.9. So 8.9. And then a comma. Comma is right above your 7 key. and then the number of compounds per year. So that one's compounded monthly, so that's 12. So to find the effective rate of 8.9% compounded monthly, we do EFF 8.9 comma 12, and we get 9.272. So that would be the percent change in the loan amount from the beginning of the year to the end of the year. So that is the effective rate of that loan. All right, let's do the same thing for 9%. So apps, finance, up to EFF. So 9%, and then a comma, and semi-annual, so that's 2. And we get 9.203. And so what we see here is that you would actually pay less interest with the 9% loan, compounded semi-annually, than you would with the 8.9% compounded monthly. And that all has to do with the frequency of compounding. Because the 8.9% is compounded monthly, the compounding actually means you're actually ending up paying more money over the course of a year. So in this video, we've looked at simple interest. We've looked at continuous interest. We have looked at interest compounded a finite number of times, and then APY and effective rate. So we've covered quite a few topics. As a reminder, simple interest we use when it is not compounded. Continuous interest we use when it says that interest is continuous. And then the TVM solver we're going to use when it's compounded a finite number of times. And then the effective rate function, we'll use that anytime it says to find the effective rate or the APY if we are given a rate that we want to convert to one of those things. All right, that's it for this video. I'll see you next time.